This video is going to cover thin wall pressure vessels. Thin wall pressure vessels are pretty much just as they are. They are vessels that have a liquid or a gas pressurized inside, and they have very, very thin walls. So when you hear the words thin wall pressure vessel, a really nice example that's of the modern era that uses these equations is the Coke can. Those Coca-Cola cans actually have the thinnest amount of aluminum that they could possibly get away with in order to keep the pressure of the can intact. And there's a really simple, easy equation for this, and that is that the radius over the thickness of the walls has to be greater than or equal to 10. Now, this is very specifically the inside radius and the wall thickness. And you must satisfy this equation in order to be able to use the equations of thin wall pressure vessels. So for a cylinder, technically we have two directions, and for a sphere, we have the same thing in all four directions. So for our cylinder, we can go out in the longitudinal direction, and this is the longitudinal stress. We can also go around the circumference of the cylinder, which would be called our hoop stress. Now, of course, in a sphere, though, there's no such thing as hoop or longitudinal because it's a circle and it goes the same in every direction. And that stress is going to be the longitudinal stress. So we have two equations, one for longitudinal and one for hoop, but they're really not actually that different. The longitudinal stress, the equation is P times R over 2 times T, whereas hoop stress is P times R over a single T. So the longitudinal stress, P stands for pressure. That's the pressure of the liquid or the gas inside of the vessel. R again is the same inside radius, and T is again the thickness of the wall. So that's all that there actually really is to it. So really, we just need to get down into an example. So on this example, we have 4 shells kind of stuck together. We have these 2 shells on the outside that are hemispheres here. We have little semicircles that are going to be attached together. And then we have these other 2 ones, which are also, this is a giant cylinder, right? So it's a cylinder with circular caps on the end to make it look like a pill. So we have that top shape, which is a semicircle effectively, but in a longitudinal direction. And we have this one, which is also a semicircle, but in a longitudinal direction. Along those black lines that connect the pieces are technically bolts that are going to hold it together. These bolts have a strength of 1.25 gigapascals. They have a diameter of 25 millimeters. The tank itself has an inside diameter of 4 meters, and the stress that the tank can hold, that the material that it's made up of, is 150 megapascals. The pressure that's inside the tank is 3 megapascals. We want to know what's the wall thickness of the tank. And then, because it would be even cooler to go a little step further, what's the bolt spacing along the X direction seam? We're talking about this seam right here. How many bolts do you need to keep this tank from exploding apart? So that one's kind of cool. So step number 1, we should always check to see if we're actually a thin wall pressure vessel. Because if we don't qualify as a thin wall pressure vessel, you can't use these equations. So, well, again, that equation is radius over thickness of the wall, again, inside radius. Well, we know our inside radius, but very specifically, we don't know what the actual wall thickness is. So is it greater than 10? We don't actually know. So we just have to assume that we are. And then we'll come back and check. So again, we're making all of these assumptions first. And again, our hoop stress is P times R over thickness, and our longitudinal stress is equal to P times R over 2 thicknesses. So we have 2 equations. We're going to plug it into both. Again, because we're technically a cylindrical tank. If we were just looking at a spherical tank, we'd only have longitudinal stress. But because we're a cylinder, we have both hoop and we have longitudinal. So we're going to plug our information into our equations. So again, the stress of our tank, 150 megapascals. So in each one of these, we have 150 megapascals. Then we have P. What's our pressure? Our pressure is 3 megapascals. So our pressure we're going to put here in green is 3 megapascals in each one of these equations. Then radius. Again, it's inside radius. And we did actually have an inside diameter, so that makes it pretty easy. And that inside diameter was 4 meters. So all we have to do is divide that by 2, and we'll get a radius. So again, it's 4 meters, but divided by 2, now it's a radius. Again, on both sides, both of our equations here. And then lastly, divided by our thickness, or divided by 2 thicknesses. So now we're simply going to solve for thickness. And if you're looking at the units, you're seeing that our megapascals are canceling, and we've got meters. So that's going to be a little bit awkward, but it's not too bad. On the one equation, we're going to get 0.04 meters. And the other equation, we're going to get, who would have guessed, half that. We're going to get 0.02 meters. So at this point, which one do you pick? When we say we're looking for the minimum wall thickness, do you just pick the small one? Well, a nice idea to remind you of is, again, Coca-Cola tried to make the thinnest can possible. And if you get too thin, it's going to rupture. So just because this guy satisfies one equation, he's not, if you plug him in over here, he's not going to satisfy it on this side. So technically, we're going to use the thickness of 0.04 meters. And again, now that we've checked and we've solved for our lovely thickness, we need to go back and verify, can I even use these equations, right? Because we assumed that we were okay. Should never assume, right? We always have to check our assumptions at the end. So again, we have our radius over thickness of the wall. Our radius, the inside radius, 4 meters divided by 2. The thickness we literally just found to be 0.04 meters. Do make sure you're looking at your units. If you start talking about one thing in meters and the other in millimeters, that's not going to give you a unitless number. It has to be unitless. It has to be a ratio of the same units together. Has to be greater than or equal to 10. So this is actually going to give us 50. And 50 is, of course, greater than 10, so good. Our assumption was correct. So our minimum wall thickness that we're going to use, 0.04 meters, which is, again, 40 millimeters. And that's question number 1. That's the easy part. If at this point you're going, wow, thin wall pressure vessels really aren't that bad, you'd be absolutely correct. However, we wanted to make it cooler. We wanted to now find the bolt spacing along the seam in order to make sure that this thing doesn't blow up. So we take it a step further because, again, how are you actually getting the liquid or the gas pressurized inside of a closed vessel? Yeah, that's definitely not going to happen. So it has to be, assembled in some way. So because of that, we're going to have some bolts. So let's actually draw a pretty picture of what we're looking at here. We just found this semicircle piece, right? We're looking along that X direction seam. So that X direction seam is going to be breaking our 2 semicircular pieces in the longitudinal direction. So effectively, this is what we're looking at as far as our shape. And we're looking at this seam right here. So again, we have a pressure, right? This pressure that we had, this 3 megapascals of pressure, that's existing all inside of this tank. So technically on the surface, we're going to have our pressure of 3 megapascals around the whole entire thing, and also in the middle on the bottom, right? So it's a pressure, it's over an area, right? Pressure is force over area. if you look at it, its units are in megapascal, which again is a force per an area. So it's acting across that entire, and it doesn't really have a surface, right? Because it's just like the floaty in between space. So what's the force? What's the force? We can just imagine that there's going to be a force here at the center of this surface, this non-existent surface, and that's going to be our resultant force. So how are we going to find that though? Because if you recall, again, a pressure or a stress is a force over an area. And whereas we do actually know the diameter of the tank, the inside diameter was 4 meters. Cool, that's the width. What's the length? Right? What's the other direction? What's this way? We don't even know. So we can't even really look at it as an area. Instead, we have to just say, we're going to have to look at it as a per meter interval. So we're just going to have to kind of look every now and then. So our pressure, again, we said 3 megapascals. Now, a megapascal is what? 3 times 10 to the 6 pascals, and a pascal is a Newton per meter squared. And again, that's going to be equal to our force resultant, the force that we've got to use all of our bolts to hold, over the area. And our area, we said, was 4 meters, effectively per meter, right? So it's 4 times whatever our thing is. So again, a per meter interval length. So okay, so we're going to get a force resultant. So our force resultant that we're going to get is going to be 12, right? 3 times 4, magic. 12 times 10 to the 6. And it's in newtons per, of course, per meter of length, right? So it is technically newtons per meter, but this per meter thing here is just a length that we're going down the entirety in the x direction. So the bolts here, these bolts that are holding the seam together, the bolts have to hold our force resultant. Okay, they have to resist this force. So again, our force resultant is going to be resisted by the total number of bolts times the force of each bolt, right? So this entire force has to be resisted by the bolts. So each bolt can take a certain amount, and then the number of bolts is going to multiply together to give us the total force resultant. What do we know about our bolts? Technically, back up here at the very top, we had a little bit of information about our bolts. They had a certain stress that each bolt can take and a diameter. Well, again, what do we know about a stress? A stress is equal to a force over an area, right? So the stress of a bolt is equal to the force of a bolt divided by the area of a bolt. Well, good news, we actually have some of these things, right? So we said that our bolt stress was, got to go back upstairs and look at it, right? Zoom out just a little bit. It was 1.25 gigapascals. So we have 1.25 gigapascals. That's times 10 to the 9th pascals, which is a Newton per meter squared. And this is again going to be equal to the force of the bolt, which we have written over here in blue, which we don't know, is the force of the bolt divided by the area of the bolt. An area for a circle is pi over 4 times d squared. Well, what's d? Let's go hike it all the way back up to the top. The diameter of our bolt, 25 millimeters. Okay, so but millimeters isn't very good for us. So let's maybe turn that to meters. So that's going to be 0.0 0.025 meters, right? There's 25 millimeters squared. So what we're going to get now is obviously we can solve for the force of the bolt. And the force per bolt is going to be 613,592 newtons. Okay, that's pretty significant, you might think. But that's per bolt. And again, we have a force resultant is equal to the number of bolts times the force of the bolt. And as you recall, we calculated our force resultant. So we can easily plug that in, right? Our force resultant, we said 12 times 10 to the 6 newtons. Technically, it was a per meter of length. Just going to keep that around here. And that is equal to the number of bolts that we have. God knows what that is. The number of bolts times, of course, the force of our bolt. And the force in each bolt, 613,592 newtons. So cool. So technically, and this is again in a per meter length, we've got, solving for N, the number of bolts that we're going to calculate is equal to 19.56. And again, this is bolts per meter length, right? But technically, when we're looking at this, we're looking at not just one side, we were looking at two sides. So this is bolts on both sides. If I just want how many bolts there's going to be on one side, first, we got to round. You can't have 0.56 of a bolt. You either have a whole bolt or you don't have a bolt. So our option is 19 bolts or 20 bolts. So ask yourself, if I put more bolts, is that going to be a bad thing? If you use more nails to hang up a picture, yeah, your picture's less likely to fall down. So in the case of my thing exploding here, more bolts is definitely a good thing. All right, so we're going to round up, and we're rounding up here to get to 20 bolts on both sides. So if I want to know what it is on a particular side, then obviously divide by 2 because there was 2 sides, and we're going to get a grand total of 10 bolts on one side. But again, it's a per meter of length. So again, what did they actually ask us for? They asked us for the bolt spacing along the X direction seam. So our bolt spacing is going to be 10 bolts per meter along our X direction seam. So does it get a little bit more fun? Sure. Is the thin wall pressure vessel part of that really hard? No, I would say it's pretty easy. Anytime you're going to do a rounding thing though, you should always check your work. If you can't reasonably think through it and go, okay, which one of these answers is actually going to make perfect sense to me, then go back and plug your answer back in. If you wanted to use here the thickness of 0.2 meters, if you plug that back into your equation and say you have a pressure and you have a radius over a thickness, you're obviously going to get a stress. If your stress is greater than your allowable, then obviously that's no good. So then you know you picked wrong. So when in doubt, always, always, always check your work. But that's all there really is to thin wall pressure vessels.